Hello everyone, welcome to Math 1350, more on math. Today's exciting lecture, we're now beginning Chapter 7, Section 1. Section 1 deals with terminating decimals. As you can guess, Chapter 7 deals with decimals, percents, real numbers. So, first section we're going to look at terminating decimals. Now, this is important because by the 4th grade, approximately, the student's supposed to be able to use decimal notations for fractions, with denominators of tens and hundred. They can also rewrite a decimal like 0.62 as a fraction, 62 over 100. They can describe length of an object as a decimal, let's say 0.062 meters. And they can locate 0.62 on the number line. So it's a lot of responsibility for us. Let's look at this. What defines decimals? Okay, here's our decimal. When we write them out, the decimal is replaced by the word and. Okay, on the left, we have the ones. Remember, our system is called the decimal system. Deci means 10. So we go from 0 to 9. Or 1 to 10. Those are our digits go from 0 to 9, but we'll go from 1 to 10 spaces, locations. So the first one, we start with ones. Because it's decimals, that means it's base 10. So 10 to the 0 is 1. 10 to the first is a 10. 10 to the first power. 10 to the second, that's 10 times 10, that's hundreds. You notice all I'm doing is adding 1, 10, basically what I'm doing is multiplying. This is 10 times 10 to the power 0 is 1. 10 by itself, 10 times 10, 10 times 10 times 10 is 10 to the third. That's the tens, hundreds, thousands, and so on and so forth. The next one will be 10 to the fourth, which is 10,000. 10 to the fifth would be 100,000. That's to the left. We know we're multiplying by 10 each step. It's just the opposite when we go to the left, to the right, I mean. On the right, we don't have oneth, we have tenth. Everything on this side ends in a th. So this is the tenth. Since it's to the right of 0, it's -1. Basically, it's whatever the number is divided by 10. 100th is 10 to the -2. It's whatever number is divided by 100. So 10 to the second is 100. But now, since it's on the bottom, it's a negative exponent. I'll discuss that later on. But these are really what's happening. Then next is the thousandths. That's 10 to the third, -3rd, which is x over 1, 0, 0, 0. So if you notice, the number of zeros, the exponent represents the number of zeros we have in our number. So 10 to the second is 100. 10 to the first is 10. It only has 1 0. It goes the same way if it's a negative exponent. It's 1 over 1 0. On the bottom, we have 2 zeros. On the bottom, we have 3 zeros. And so on and so forth. So this is the 10th, 100th, thousandths, 10 thousandths, 100 thousandths, and then so on and so forth. But these, if it ends in a th, we know it's a decimal. By the 5th grade, the students can read and write decimals. To the thousandths. Using what we just discussed, base 10 numbers. Now I just use the name numbers, but we know their names. Thousandths, 100 thousandths. And by the expanded form. The expanded form is pretty interesting. It's actually how we really used to write numbers when we first in school many decades, centuries ago. The number 347.392. Each one of these numbers are represented by these locations we have here. Remember, there's a decimal. So the first one is 3. This one is 3 times, since it's in the 3rd place, times 10 to the second. And I'll show you what that means in a second. The next number is 4, since it's in it, 10 to the first. It's the next one, 7 times 10 to the 0, which is the ones. Plus, this was 3 times 10 to the -1, because it's one space to the left, plus 9 times 10 to the -2, plus 2 times 10 to the -3. So let's see what this really means. 10 times 10 is 100, so 3 times 100, plus 4 times 10, plus 7 times 1 is just 7. 3 over 10, that's that one. 9 over 100, that's that one. And then 2 over 1,000. So this number is read 347 and 3,000 392 thousandths. So it's 347 and 392 thousandths. Whenever you read the decimal part, it's always the very farthest right number. Whatever location that is, that's the name of that expanded form number. Okay, there are different ways we can represent these numbers when we teach kids. Representing terminating decimals. What that means is the terminating simply means that they either end at a finite location, like 2.35 or 4.1117. It comes to an end. Or if it's terminating, it can be repeated. Like 2.111. It keeps on going, so we write that 2.1 bar. 34.272727. It'd be 34.27. Or the repeating could be, let's see, negative 3, 1, 2, 4, 5, 4, 5, 4, 5, and so on and so forth. So we would write 3.1245 and put the bar over. So whatever the bar is over, those numbers repeat forever. It could be a single part, or it could be a long segment of it. So be very careful when you read those things, that's what they mean. So we look at using the cubes. Remember, in the past, if we had a big sheet, those were the hundreds. The single bars were the tens, and the single units were the ones. But now, in decimals, we look at a block. It has 100 little dots in it. It has 100 cubes. These are our ones. If we have that, then the sheet of those it's made up of each individual sheets. One sheet is 1/10 of those, and one strip of those is 1/100th, and then the one small cube is 1/1000th. That's what would represent them. Or if we're introducing them for the first time, if we have 10 cubes in a strand, this is 10. We can introduce one of these cubes as 1/10. So if you had bar are 3 bars and 4 single pieces. So this would be 3. This would be 4. Not just 30 plus 4, so this would be 30 plus 4. But the way we look at this, since we're looking at one, so this is 4/10. There's 3 of these big ones and 4 of these individual ones. So it'd be 3 and 4/10. Or 3.4. Yeah, so I mean, make sure that whatever you introduce these to your students, that they follow the same rules and patterns. If you want to use your own rules, then you can do that, but be consistent with it. Let's look at converting fractions to decimals. Here we have our decimals. The expanded fractional form, or what it means, and then the common fraction notation. That's what we use nowadays. For example, let's say we had 5.3. The expanded form, since this is the ones, and this is the decimals in the tenths, we write it as that. The common notation is we would add the top numbers and over the tenth. So it's 53/10. Also with negative numbers. The negative belongs on the outside. So it's 3 plus 6/10. Which is negative 3/6, or negative 36/10. This one is also 5/3. Sorry about that. I picked the wrong time to start this. So, 25/10. This is how do we do that? And we'll come back to this. We're doing decimals first. So as we had 20103. All right. So we have the 2. There's 0 in the tenths. There's a decimal. There's a tenth. There's 1 in the hundredths. There's 0 in the thousandths. And there's 3 in the 10,000ths. So since the 2 is in front of the decimal, it would be 2 and 103 10,000ths. Or we can look at just the top numbers. We have 20103 over the smallest decimal is 10,000. Right. Let's look at converting fractions into decimals. So 25 is this 2 times the 10 plus the ones, all over 10. Because it's addition, we can split them up, so it's 2 times 10 over 10 plus 5 over 10. These cancel. So we have 2 plus 5 over 10. Since that's in a decimal, it's over 10. We know it's a decimal location, so it's 2.5. It's the first decimal location. $56 over 100. And now we have 5 times 10 plus 6 over 100. Now split them up. 5 times 10 over 100 plus 6 over 100. Cancel one of the zeros, so we have 5 over 10 plus 6 over 100 equals, this is a denominator, which is a decimal there, the first location, the second location. There, close the window so they can't see, they can't bark. Alright, let's look at another one, a bigger one this time. 205 over 10,000. So this is 2 times 10 ones, tens, hundreds, so that's 2 to the second. 0 times 10 to the first plus 5 over 10,000. Two times 100, that's what that is, over 10,000 plus 0 plus 5 over 10,000. 1 0 cancels, so it's 2 over 1,000. 0, 5 over 10,000. Since these are fractions, we know there's a decimal. We start at the thousands, so it's the tens, hundreds. We have a 2 in the thousandths location. A 0 and then 5 over 10,000. I had too many zeros there. So it's in hundreds over 10,000. So this is 200. 2 zeros. Okay, 2 zeros cancel, so it's the hundreds, not the thousands. Yeah, so it's 0.0205. Plus 2 zeros cancel, so you're over 100. Tens, hundreds. Okay, let's look at expressing our numbers as decimals. Express as decimals. Basically what that means is, what you have to do is you have to make, if possible, make the denominator a factor of 10. So for example, if we had 7 over 2 to the 6th. So what do we have to multiply on the bottom so it's has to be to the power 6. But what times 2 equals 10? 5 to the power 6. Whatever we multiply to the bottom, we have to multiply to the top. So now on the bottom we have 2 times 5 is 10, and they're both to the power 6. 5 to the power 6 is 15,625. 15,000 times 7 is 109,375 over 1 million. So if it's a positive exponent, 10 to the power, what that means is that there's a 1 and this many zeros. There's 6 zeros. So now when you divide it, when the big number's on the bottom, what that does is this number of zeros tells us how many decimal places we move to the left. 1, 2, 3, 4, 5, 6. So the answer is 109375. So the way you would read this is 109,375 millionths. Because that's a million. Okay, well, if we had an equation like this: 2 to the third, 5 to the fourth. So what do we have to multiply the top and bottom to make equal 10? There's 3 2's and 5 4's, or 4 5's, I mean. So what we need is one more 2. We need one more 2. Because now 2 to the third times 2 to the first is 2 to the fourth, times 5 to the fourth. 1 times 2 to the first is 1 times 2. It's just 2. Now what do we have on the bottom? If we have, look on the bottom, 2 times 5 is 10, and they're both to the power 4. So we have 1, 2, 3, 4. 2 over 10,000. Which means we move 1, 2, 3, 4 spaces, the decimal 4 to the left. So we have 2. 1, 2, 3, 4. So it's 2 with 3 zeros in front of it. So that's the pattern we're looking for, if possible. So if we had a number like this, 1 over 125. The first thing we have to do is factor out the bottom. So we know it's factored out of 5. 5 goes into 12 twice, with 2 left over. 5 goes into 25, 5. 25. So we have 1 over 5 cubed. So that's what that equals. So now what do we have to multiply top and bottom to make it equals 10? 5 times 2, but since we have 3 5's, we need to have 3 2's. Again, we're multiplying by 1, plus 2 to the third over 2 to the third, they cancel out, equals 1. 2 to the third. 5 to the third times 2 to the third is 10 to the third. 2 to the eighth, 2 to the third is 8. 2 times 2 times 2 is 8. And 3 zeros. So we have an 8. Move it 3 spaces to the left. So it's 0.008. So far so good. Let's try another one, a bigger number. 7 over 250. Factor out the bottom. Since it ends in a 0, we know there's a 10. and 25. So 10 is made up of 2 times 5, 25 is 5 times 5. So the bottom is 2 times 5 cubed. We have 1 2 there now. How many more do we need? We have to equal 3. So we need 2 more 2's. So we have 7 times 2 squared. 2 to the third times 5 to the third is 10 to the third. 2 squared is 4. Is 28. 7 times 8. 4 is 28. So we have 28 with 3 zeros. The decimal is right here at the end of 8. We have to move it to the left 3 spaces since we're dividing. 1, 2, 3. So the final answer is 0.028. Defining terminating decimals. Nope. Not every rational number, remember, fraction, not every rational number can be represented as a terminating decimal. For example, 2 over 11. It can't, because the bottom cannot be represented as a factor of 2 and 5, or factor of 10. Not terminating because 11 cannot be written as a power of 10. There's all the other examples we had. We always had on the bottom 10 to the power something. All right, so that leads us to our first theorem of this chapter. Theorem 7-1. A rational number, a over b, in simplified form, or just take as far as you can down. A rational number, a over b, can be written as a terminating decimal if and only if the prime factorization of the denominator contains no prime numbers other than 2 or 5. So a rational number, a or b, cannot be written in as a terminating decimal unless the bottom number can be factored out in only factors of 2 and 5. No other prime numbers can be down there. Let's look at some examples. 7/8. Does that have terminating decimals? Well, let's see. 4 times 2, 2 times 2. So 8 is 2 to the 3. So yes, since the bottom is only in factors of 2. (11/250). 250 is 25 times 10, because it ends in a 0, it's times 10. 25 is 5 times 5. 10 is 2 times 5. So the bottom is 2 times 5 to the third. So yes, it can, because the bottom's only 2 and 5s. (21/28). Can that be written as a terminating? Well, let's find out. 28, 2 times 14. 14 is 2 times 7. So we have 2 squared times 7. So no. Cannot be written in terminating decimal form because of that 7. Alright, let's try a much bigger one. So in other words, this is what's called prime factorization. I take whatever number, I break it down to its smallest prime numbers. So that's called prime factorization. Let's try one last one. 37/768. 768. 2 goes in there because it's an even number, so 2 goes into 7 3 times with 1 left over. 2 goes into 16 8 times. 2 goes into 8 4. Alright, so we know since it ends in even, 2 goes in there. 2 goes into 3 once with 1 left over. 2 goes into 18 9 times. 2 goes into 4 twice. Again, ends in a even integer, so it's divisible by 2. 2 goes into 19 9 times. 2 is 18, so it leaves 1 left over. 2 goes into 12 6 times. Ends in even, so it's divisible by 2. 2 goes into 9 4 times with 1 left over. 2 goes into 16 8 times. We're looking good so far. 2 goes into 4 twice. 2 goes into 8 4 times. 2 goes into 2 once. 2 goes into 4 twice. 2 goes into 12 6 times. All because of that 3. No. Cannot be written in terminating decimal form. That sucks. We went through all that work. Ordering terminating decimals. Which one's larger than the other? By 4th grade, students should be able to compare two decimals to the hundredths place by reasoning. Their size and recognizing that comparisons are valid only when two decimals or refer to the same whole number. What that means is they have to have the same denominator. So in order to compare two decimals or two fractions, they have to have the same denominator. 0.42, compare that to 0.71. Well, 0.42, since it's two decimal places, is 42 over 100. Same thing, 71 is 71 over 100. Since they both have the same decimals, which one's bigger? We know 71's bigger, so we give it that sign. And if you have a series of numbers, compare digit to digit to digit. There's 0.1135 as opposed to 0.1134, 0.11391. Yeah, so they all have the first set of numbers. So the bigger number, this is the biggest, the next, and the smallest. Because compare number by number. All right, so let's get ready for the homework. Thank you. Bye.